All right, in this section, we're going to look at distributions of sample means. So we're going to start here for a population where the distribution of the individual elements X are normally distributed and the samples of size n are randomly selected. The following statements must be true. So again, kind of understanding what we're talking about here, we have a population and it has that normal bell curve distribution that we're drawing from. And what we're going to do is we're going to pick samples of size n. So, and probably when we take a sample, we're going to get a lot of values from the middle here, but we'll get a few from the edge, and we might get one rare that has a bunch of samples over here or something. But we're taking samples of that from the population, a normal distributed population. Okay. And the following has to be true. The distribution of sample means is normal. So what's happening here is we take a sample and we calculate its mean. And then we take another sample and we calculate its mean. And we take another sample and they're all the same size samples. And we calculate its mean. And we take another sample, calculate its mean. And if we could do that for every possible sample that we could get from that normal distribution. So remember, the original one had that bell-shaped curve. But if we looked at all these mean values and made a list of them, what we would find is that would also form a normal distribution. That would also form a normal distribution. Again, because when you take a sample, you're more likely to pick things from the middle. When you calculate its average is more likely to be in the middle. So you're going to kind of clump up in that middle area. The mean of this population, the mean of the distribution of means. So the mean of the mean, right? This is the mean of the sample means, right? The mean of the mean, the mean of the sample means is going to equal the original population mean. So whatever that original population was, what its average is, its mean is, that's going to be the same number as if you take the average of all the average values. That's going to be the same. So this mean here, we're going to say that's the mean of all the sample means. This is going to equal the population mean. That's what this is saying. So if you look at all the possible averages you could get, or all the possible sample means you could get, and you were to plot those, you would get a normal distribution. And where that's centered at is exactly where the population center is at. But you can already start making making connections here, that if I could get enough samples, I could get an idea what the real population mean is from that. You can see where the gears are starting to turn there. Now the standard deviation for all the sample means is not going to be the same as the standard deviation for the original population. So this one is the original population standard deviation. Population parameter, right? And this is the standard deviation of the means. Okay. Instead, it's going to be usually some lower number. Take the standard deviation, divide by the square root of your sample size. How many? And the bigger the sample size, the smaller the standard deviation is going to end up being. So you can think, as you get bigger and bigger sample size, your bell curve here, where I'll draw it here, is going to get steeper and steeper as n gets bigger. You can think about, what if I had a sample size that was exactly the same population size? it would be right. The mean of it would be right on the normal mean, and that would be it. That's all you would have. Okay, so some notation here, some formulas. Again, the mean of the sample means. Excuse my handwriting here. The mean of the sample means is going to equal the original population mean. That's what this is saying. Okay. The standard deviation of the sample means is going to equal the original population standard deviation divided by the square root of the sample size. And one thing you might be wondering is like, why are we using sigma here instead of S? So there's layers here, right? So you have the original population, right? Some group, and it's got a mean and a standard deviation. Then you take a sample from there, and that sample has a sample mean and a sample standard deviation. But what we're saying is we're going to take this and we're going to create a population of samples. It's going to be all the possible samples. And so in that population, I guess I can go that way. In that population of samples, it has a population mean that's based on the sample means, and it has a population standard deviation that's based on the sample means. So each individual sample has its own mean and its own standard deviation, but this is the standard deviation of all of them grouped together as a population. So that's why we're using sigma there. All right, and then you can kind of see where this is going. We're going to go to, okay, I have this new population. This is the population of average sample averages, sample means. And what we're going to, it's a normal distribution. And so we're going to convert it to the standard normal values using the z-scores. And so we're going to use its mean and its standard deviation to do that conversion into z-scores because it's its own population based on the original. Now, doing some substitution here, you can replace, we said the original population mean and the mean of all the sample means is going to be the same. So you could replace that. And then from this formula, we could replace the samples, or sorry, the population standard deviation of the sample means. And we could get this formula, which you don't divide by fractions, we multiply by the reciprocal, manipulating that around, you get this formula. I would not use these formulas. I would use this formula and just calculate this and just replace this with mu because they're the same thing. But you could do that algebra if you wanted to try to do that calculation directly from the original values. If you didn't want to calculate the standard deviation of the sample means, if you didn't want to do that calculation, you could use this one. I wouldn't. I would use the original one. All right, so let's look at an example here. We're going to look at page 329 in your book. Number 16 has to do with white blood cell counts per cubic milliliter. And we're told that it's approximately normal. Great. We're told that the mean, with a mean of 7,500, and they estimate the standard deviation to be 1750. And it's going to talk about that if you get a test result where x is less than 3,500, that might be a sign that there is a viral infection affecting the bone marrow. Okay, so we're going to calculate some things here. So on step one, or sorry, part A, what is the probability that on a single test, X is less than 3,500? So what's the probability that X is less than 3,500? Now, understand what's going on here. Single test. This doesn't have anything to do with population means. So all this stuff we've talked about so far, not relevant, not yet. This is old. This is stuff we've been doing in the last part. So first thing we're going to do is we're going to convert this X value to a Z value. Because remember, the original population is a normal distribution, so we can convert it to the standard normal distribution. So we're going to do that normal Z value calculation. You know, what's the probability I take one test and I get this value? And the idea is you could be a totally normal, healthy person and still get a, you know, some extreme value. A normal person could still get it. It could just be, you know, like a false positive or something. So what's the chance that would happen? That's what we're calculating here. So we do that calculation, 3,500 minus 7,500, and then divide that by the standard deviation, 1,750. And we get this, and we're going to round this to 2 decimal places because that's what our chart, we're going to look at our chart here. That's a 9. So negative 2.29. Let's go to our chart. And again, we're looking at these charts here. All right, so I'm going to change this into Z's. What's the chance that we are less than negative 2.29 standard deviations below the mean? All right, and so I look at that table. Remember, that's how that table is set up. It's set up to go from that, whatever that Z value is, down. So great, that's going to work just fine for us. Negative 2.29 goes at the end of the table. It looks like 0.0110. So a little more than 1% chance that you would get a normal healthy person would get a value down there. All right. So pretty unlikely. If you were working in the medical field, you probably say, whoa, hello, that the flag's going up there. All right, so we're going to B. Suppose a doctor uses the average. Okay, so now we're in today's stuff. We're in 6.5 material. Suppose that the average X bar for 2 tests taken about a week apart. What can we say about the probability distribution of X bar, of the sample means? Well, since the original population is normal, this distribution should be normal. Okay, should be, say, this distribution, even though we're only using 2 values to calculate the average, this distribution should still come out to be a normal distribution. So with that in mind, what is the probability that this average would be less than 3,500? So again, we're all in averages now. So we need to do a couple of things. First thing we need to do is say, what is sigma of this sample means? And so that is sigma over the square root of n. We go back to the original one, 1,750 over the square root of our sample size. And for this problem, we're looking at a sample size. I should write this down. N equals 2 tests. So n equals 2. All right, so we're going to put that in there. We're going to calculate our new standard deviation, 1,750 divided by the square root of 2. And that is about 1237. That's our new standard deviation of our population of our means. Okay, so that means I need to find a new Z value. My Z value is going to be 3,500 minus 7,500 over this. It's called the standard error, 1237. So let's look at that. 3,500 minus 7,500 divide by 1237. Now we're at a Z value of negative 3.23. So let's see what happened. we had one value and it had a Z value of negative 2.29. But now we got two and we're at a Z, we averaged those two and we got in, now we're looking at the average of them and it's at a Z value of 3.23. So by having two, we've made the Z value higher, which means there's going to be less, I guess here, less that way, because we're at a bigger Z value. So again, we're gonna, the question is, what's the probability Z is less than negative 3.23? Looking at my table, negative 3.23, the chance that would happen, 0.0006. So 0.06 of 1% chance that would happen on two tests for a totally normal human being. So, you go in, the doctor does this test once, they say, oh, well, there's only a 1% chance that would happen. I want you to come back on Tuesday and we're gonna do the test again. You come back on Tuesday and it comes out another, they average those two tests together and they end up down below there and they're like, that's probably, you're probably suffering from this. We need to start dealing with it right now. If it's some kind of infection thing, get rid of that infection. All right, let's go on. C says, let's do what we just did, but this time, now we're going to use an N value of 3. We're going to do 3 tests and see what that is. So again, what's the probability that X is less than 3,500? We need it, now that we have 3 tests, that's going to change our standard error. So that's going to be 1750 over the square root of 3. So 1750 divided by 3 square root, 1010. That's how big a standard deviation should be for sample size of 3. So what's our new Z value? 3,500 minus 7,500 over 1010. 3,500 minus divided by 1010. Negative 3.96 is going to be our Z value. So what's the probability X is less than negative 3.96? So we're going to look at our table here, and our table doesn't go that low. The most it goes is negative 3.49. So we're just going to have to say it's less than 0.0002. It's less than that. That's the most we can say. We can't say exactly what it is because our table doesn't go that low, but we know it's less than this. It's less than this. So, it's even more remote. If you took 3 tests and that averaged out to be there. Okay, so D asks us to do an interpretation. Compare your answers to parts A, B, and C. How did the probabilities change as N increased? Probabilities got smaller, right? Right, we went from what, like a little bit more than 1% chance a healthy person would get that value to 0.06 of a percent to less than 0.02%. So yes, as this number of tests you take, and you keep your average of those tests is still down there, then it's very unlikely that's going to happen. So the more tests you take, the more unlikely you're going to get those extreme values, unless this is not a normal healthy person. How did the, let's see, how did the probability change? Okay, the person had an average of less than, a sample average of less than 3,500 based on 3 tests. What conclusion would you draw as a doctor or nurse? Person is ill. I'm just going to say that, it has the viral infection. Okay, so you're just going to, it's very unlikely that would happen after 3 tests. All right. I would like you to do problems 13 and 15. They're very similar to 16. And pause the video, go do them, and then come back. Okay. So assumed you paused the video, you worked out those problems, very similar to what we just did. Let's go on. All right, central limit theorem, regardless of the distribution of the original population. So at what we just talked about was if the original population was a normal distribution, we somehow knew that from experience or whatever, we have a normal distribution. We could basically work with any size group, any size sample size, and it would be good to go. You know, we could say, oh, well, if I look at the average of the means, then it's going to be normally distributed. Now, this says, well, let's assume it's not a perfect normal distribution. Maybe it's close, or maybe, you know, maybe it's still mound shaped, but it's not exactly a normal distribution. Maybe it's skewed a little bit or whatever. This says that if you pick samples that are large enough, and what we found is that's at least size 30. You go with samples 30 or bigger, then you calculate the average of those samples, and that will be normally distributed. But you got to have samples of size 30 at least. If you can't guarantee the original population you're drawing things from is a normal distribution. Again, it could be close, but if it's not normal, doesn't have no symmetry to it, then you should work with size 30 or bigger samples. That's what this is saying. And then if you do, then all those other features we just talked about. So you could have the original population, you know, maybe it's bimodal, something like this. And as long as your sample size was at least 30, then for the mean, so this is for your normal values, your raw values, and this is for your sample means, it would come out to be a normal distribution. All right. So let's look at number 6 on page 328. So suppose X has a distribution with a mean of 20, great, and a standard deviation of 3. And we look at samples of 36, so that's bigger than 30. So it doesn't really matter about what the original distribution was. This, because we have more than 30, the mean, the distribution of the sample means will be normal. And that's a way you can convert non-normal things into normal things, by looking at the sample means. All right. A. Describe the sample mean distribution and compute the mean and standard deviation of the distribution. So again, it should be normal. Okay, that should be the distribution, and then compute the mean. So the mean of the sample means is 20. Again, it's the exact same thing as the population mean. That should happen. And then the standard deviation of the sample means should be the original sample mean divided by the square root of your sample size. So 3 divided by 6, 0.5. Should have a standard deviation of 0.5. All right. Find the z-value corresponding to a mean value of 19. This is not regular x, it's a mean value of x. So we're going to use this. This is why they asked us to calculate those. So a mean value of 19, our sample mean, or yeah, our sample mean, our mean of our sample means is 20, and then our standard deviation of our sample means is 0.5. So -1 over 0.5 should come out to be -2. How many times does 0.5 go into 1? Twice. So if you're not doing it on a calculator. All right. And I'm just going to do this here. I'm going to put 2.00. Now, it is -2 perfectly. You don't have to put the 2.00, but this is for the table, right? The table for z values always has 2 decimal places. So I'm putting those 2 0 zeros not because I rounded or anything, but just because it's in reference to the table. All right, and here we go. Find the probability that X bar, the sample mean, is less than 19, which corresponds to probability that our Z value is less than negative 2.00. And again, that's just how our tables are set up, negative 2.00, 0.0228, 0.00228. All right, D, would it be unusual for a random sample of size 36 from a X distribution to have a sample mean less than 19? Yes. Yeah, I would say it'd be unusual. Only a 2.28% chance that would happen. Now, if it did happen, I wouldn't be like, oh no, that's impossible. It's not that level. But there's only a 2% chance. That means there's about a 97.78% chance, 72% chance it would not work. So, or you would not get a value in there. So I would say it's not real likely there, but I would say it wouldn't totally make me believe. But I would say that's probably unlikely if you had a sample size of 36 or bigger. Okay. Bias. So let's talk about some bias and variability here. So we're going to say a sample statistic, and I think we mentioned this in an earlier chapter. It sounds familiar to me. A sample statistic is unbiased if the mean of its distribution equals the value of the parameter being estimated. Okay, estimated. All right. So what we're saying is that, like, let's say mean, sample mean. If the mean of basically what this is saying is, if this is true, if the population mean of all the sample means is equal to the population parameter, the original population mean, then we would say that's unbiased. That's an unbiased situation. Now, if you're looking at like something, that's not normal and you took a sample size of 3, you might have a pretty biased situation, because you can't necessarily say that's going to work out to a nice normal distribution. You'd have to go at least 30 or bigger. But if this does give you, if it's mean, if the mean of the means comes out to be the actual mean of the population, then that is unbiased. Likewise, if you were calculating like the mean of the proportions, and that came out to the proportion of the whole, or sorry, no hat, the population proportion, then you would say, oh, okay, that's also would be unbiased. That would be another example of unbiasedness. And we'll eventually talk more about proportions. We'll come back to those. We did those in binomial distributions, but we'll come back to it again later on. Okay, so what's variability? This is the spread of the sampling distribution. I don't know why I suddenly started acting. Sampling distribution Okay. And this is affected by the sampling method. That can affect the distribution, and sample size. Remember, the standard deviation is kind of a measurement of variation. It's not the variance, that's the square, the standard deviation, but a variation. So we saw that as you changed the sample size, that changed how spread out the data was around, that mean there. The big thing here is larger samples mean smaller distribution, or smaller variability, smaller spread, smaller. Okay. So the larger your sample, the smaller the variation, smaller the variability or the spread of it. Okay. So go ahead and work out 2, 3, 4, 5, 7, and 11. One thing I want to go back real quick. I think I kind of skipped over it because I was reading kind of fast. Yeah, I just want to, I mentioned this while I was talking, but this thing is also called the standard error of it. So this standard deviation of the means is also called the standard error. So I just wanted, I realized I mentioned it and I said it, but I didn't emphasize it when we looked at this slide. So I just want to go ahead and reinforce that. Okay. Other than that, I think we're done. So go ahead and do problem for the rest of the homework, 2, 3, 4, 5, 7, and 11. And I'll talk to you later.